Hi everyone, it's Miss Gogerty again, coming to you with another fun-filled lesson. So wish that we were live to go through this, but hopefully this will do. So just starting off, you should have the worksheet that is going along with video 6, 3.6 notes on velocity and acceleration. I'm going to say that today, this lesson is going to be a pretty, I'm hoping, key lesson for all of you who have either been in physics or are taking physics, because today is the exciting day. This video is the exciting video when all the things that your physics teachers have been talking to you about with position, velocity, and acceleration is going to really merge together with what we're doing in math. Because truly, all the things that your physics teachers want you to be able to do and physicists do wouldn't be possible without the calculus of studying rates of change. So I'm hoping to put connect a lot of dots for you today. So starting off at the top of the page, this is just a continuation off of our last video. I had asked you to please go and finish the last 3 derivations of the derivative of cosine, I believe it was cotangent, and also of cosecant. So what I've highlighted here at the top of the page is really just, hey, these 6 trig functions, you need to have the derivatives memorized. So I mentioned in my last video that I think it is super important for you to have one sheet right now that is a continuation that we are going to keep adding and adding and adding to of things you should have memorized. So at this point, you should have your limits of trig functions on there. You should probably have what's the derivative of e to the x. You should have how do you use the quotient rule? How do you use the product rule? What is the power rule? And now these 6 derivatives of our trig functions. So if you need to pause and go do that so that you don't forget, go do that. Make a sheet of notes. I suggest the last page in your notebook and get those down as easy access reference for yourself. Okay? So with that, moving forward, okay, today, our notes are going to specifically focus on instantaneous rates of change. And what does that mean? So we've already seen that instantaneous rates of change is the same thing as the slope of a tangent line, and therefore derivative. We use these terms in calculus interchangeably, okay? So I need you to be on the foreign language path right now, math foreign language path. If we say instantaneous rate of change, that means derivative, that means slope of the tangent line. Okay, interchange those 3 words. So unless we use the phrase from this point on, unless we specifically say average rate of change, the phrase rate of change means instantaneous. And I find this to be so important that in calculus, the phrase rate of change refers to instantaneous rate of change. I'm highlighting that. Please underline it, because I don't want anybody confusing when do I find average rate of change and when is it instantaneous. Remembering that instantaneous means derivative. So in calc, unless we put the word average in, you're referring to a derivative. It's instantaneous rate of change. Okay? So first thing I want you to do is to take on this example 1. I feel that you should be able to do this without me. So I'm going to pause my video. You're going to pause your video. And when you come back, all the stuff's going to be written in. So take a minute. Can you figure out the rate of change, even if it applies to area? Because remember, all of calculus is all rates of change. It's not just a specific motion, okay? So pause your video, try that example 1, and then come back. All right, so ladies and gentlemen, how did we do? So your final answer should be that crazy equation that I wrote out there. However, yours might look different, so listen closely. So first of all, they're obviously asking us to look at the rate of change of area. And so if we're trying to find the rate of change of area, then the very first thing I'm going to need is an area equation. So I'm not going to waste my time multiplying out t to the 1/2 times 2t plus 1, but if you did, you're not wrong. Okay, so I just want to specify that if you chose to multiply this equation out right here, you could still possibly be okay, all right? But the fact that it said rate of change in the problem meant right away that I'm looking for the derivative of the area with respect to time. So writing this notation dA dt means what's the derivative of our area with respect to time, or what is the change in area with respect to time. So as I went through that, I used the product rule because I left my equation as as two different functions being multiplied together, okay, or two different terms being multiplied together. If you multiplied these out, you probably would find that you were using the power rule in order to find the derivative. Both options are completely fine. I'm not going to multiply this out to find out what it comes out to being. I'm going to leave this just the way it is, which would be fine on your AP exam. The biggest thing that I want to stress before we keep going is, what is the measure of the units for this, okay? So if we kind of come back to here, you guys should all know that if we're multiplying centimeters times centimeters, right? Like this length is in centimeters, this side length is in centimeters, that our area equation is centimeters squared. So now if we're turning this into a rate of change, think about it, it's the change in area, and our change in area is centimeters squared versus time, okay? So if you're wondering where centimeters squared came from, keep in mind you're calculating slope. If we were to graph this out, this area function, change in area is going to give us this unit, centimeters squared, versus change in time is over seconds. Okay? All right, if you still have questions on that, please by all means let us know. But now we get into the fun stuff, or I'm going to call this the fun stuff. Okay? So what happens is that really, if calculus is all about studying the change in things, the rate of change, well, then we can actually start looking at the motion of different objects. Now, we can make the motions pretty complicated, which we're not going to quite get there yet, or we can keep them on a more simple, let's just talk about something that's moving horizontally or vertically, okay? So we're going to talk about motion along a line. So when we look at this, we can talk about a spring attached to a wall, stretched and then released, and that is something that's going to move back and forth, and the motion can be described as a sinusoidal or a cosine function, and I'm just saying we're not quite ready for that. However, you did look last year at writing, whenever you did your trig functions, you modeled sinusoidal graphs or sine graphs, and probably even looked at the motion of a spring moving back and forth and creating a sine or cosine graph. But we're going to start a little easier. We're going to talk about a line, okay? So something horizontal or vertical can also be described using functions. So typically we use a position function, which we call s of t. So the position or s of an object after t seconds. So let's get into some physics/math talk, okay? So let's just start with the displacement of an object. Okay, displacement is really talking about how much something has moved, but it is not distance, okay? There's very important distinction that I'm going to make right now. When we're talking about displacement, we're talking about how far something is moved, but given a direction. So this is very, very different. So displacement, or s of t, is going to be s of b minus s of a. Okay, so what I want you to think about this is that the final spot that we're trying to evaluate something minus the initial value, like the initial placement. So why this is different from distance is because distance will never be negative, right? If I walk to Niles West and I walk back home, nobody's going to say that I ended up with a distance of 0, right? However far I walked to school, then walked back home. However, the displacement would be 0, okay? Like, where did, I guess, how do I want to explain what was my final position in this? So when I'm looking at displacement, I can have a negative because it's going to indicate direction for me, okay? So distance refers to absolute value. That is not displacement, okay? So let's put it this way. If I walk to school, let's say that I walk 1 mile east, okay, that east is going to matter. That would be a +1. But if I go from school back to home, that would be a -1 in terms of displacement because now I'm walking west, okay? More on that in our example. Okay, average velocity. Okay, this is where it's going to be very important to start pointing some things out to you guys. Okay, average velocity of an object is described as the total change in position, which is displacement, divided by the total change in time. It can be thought as the slope of a line connecting 2 points on a position function. Okay, more importantly, what we're describing here is the slope of the secant line, right? Now, why is this so important? Well, notice that we said average velocity, first of all, average rate of change. So I'm looking at a rate of change as what's my displacement versus time. So if I wanted to think about this, okay, a little bit more of a general format, this would mean S of B minus S of A all over B minus A. So I'm finding an average rate of change right now. That's going to represent your average velocity. That's not calculus yet. The calculus comes in when we look at an instantaneous velocity. So basically, I've got a position, like something is moving horizontally or vertically or whatever we're talking about. And what we're trying to do now is say, hey, okay, I want the rate of change between the 2 points, but I want those 2 points so close together that they are infinitesimally close. And I'm looking then at an instantaneous velocity. What is the derivative of the position function? Okay, so we're even listing it out here that an instantaneous velocity means that we're looking at a rate of change between two values that are so close that there's the definition of our derivative, okay? Now moving forward, as I specified in the beginning of this, is that average velocity, unless we actually say the word average velocity, it's to be assumed that we're talking about instantaneous. So in other words, whenever we see the word velocity moving forward, you need to realize that that means an instantaneous velocity. So what we're looking at here is we're saying what is the instantaneous rate of change on the position function, okay? So instantaneous rate of change on S of t. That's what instantaneous velocity means. Or if you want to look at it as a progression, it's the limit as A approaches B, or as B approaches A, whichever way you want to get into this, of S of B minus S of A all over B minus A. So these two values are getting so close together, okay, we're looking at a limit, we're now talking derivative. So instantaneous velocity, V prime of t, or I'm sorry, I just said that backwards. S prime of t is V of t, okay? The velocity function is the derivative of our position. So velocity, it kind of is very, very close to the concept of speed, but we're gonna indicate there's a difference. So a positive velocity means that we have a motion, okay, but it's going in a positive direction. So we're looking at the speed, but we're giving speed a direction, okay? So positive velocity means that we're moving in a positive direction. So say right is a positive direction, up is a positive direction. Negative velocity indicates we have movement, but in a negative direction. So negative directions would be down and left. A little bit more on this in just a few minutes, okay? So let's go to the next idea. So then what's speed? Because speed is really similar to velocity, okay? Speed is the absolute value of velocity. So if I say that I'm moving 30 feet per second down, then my speed is 30 feet per second. If I say my velocity is 30 feet per second up, then the speed is 30 feet per second, okay? Velocity is powerful because it's telling you direction. Speed is just giving you how fast something's moving, okay? So velocity is a little bit more powerful for us in terms of physics and looking at the motion of objects. So let's get this down. So speed is the absolute value of our velocity function. All right. And so then last, acceleration. Oh boy. Okay, acceleration, look at that, is the rate of change in velocity. Okay, I don't need to say instantaneous. Remember, from this point on, we are fully immersed in our foreign language, and we understand that when rate of change is in calculus, it means instantaneous, unless we write the word average. So acceleration is our instantaneous rate of change in velocity. So it's implying a derivative. Once again, here it is. So if we take this a little bit further, and I say, okay, if I've got a velocity function, I've got a graph or an equation, and I want to look at the rate of change between 2 points or two specific, at a specific time period even, okay? 1 specific second, I can figure out the acceleration of an object at any given second, because that is the derivative or the rate of change of our velocity function, okay? So since it is a derivative of velocity, it's also going to be our second derivative of position. So let's kind of summarize what's happening. If I want to look closer at acceleration, okay, so if I specifically am right here, okay, acceleration is the limit on our velocity function, okay, meaning that let's find the rate of change, let's find the slope, okay, between 2 points that are infinitesimally close, that the distance between them is practically 0, okay? So acceleration is the derivative of velocity, and velocity is the derivative of position. So how are acceleration and position related? Okay, well, I have to take the derivative once of the position to get velocity. So I'd have to take the derivative of the position twice to get acceleration. Okay, and that is down here as well at the very bottom, just kind of summarizing this. All right, so last key thing before we get into some examples. So what happens if our acceleration is positive? What does that really tell us about velocity? Okay, well, if acceleration, not if, acceleration is the derivative of velocity. So if the rate of change of velocity is positive, okay, and now I just use that word rate of change. The rate of change of velocity is acceleration, right? If the rate of change of the velocity equation is positive, then that tells me the velocity had to have been increasing, right? And we're going to see that on the next page, okay? So think about this. If I have a velocity graph, and I'm just making something up right now, I have no idea, right? I don't want anybody to overanalyze, where did I get this? I just got this from my brain, okay? So here's my velocity of some object moving. If this is positive, meaning that it's increasing right now, okay, then think about if I took the derivative at any point along here, okay, until I get to the top. If I take the derivative, let's say here, or here, or here, okay, then the derivative, which is acceleration, is positive. Now what happens if we keep going and my velocity graph turns and is now decreasing? What happens to the derivative of each of these? Oops, let me get a different color really quick. So the derivative, or the slope of the tangent line, well, isn't that going to have a negative rate of change? Each of these green lines that I just drew, they're going to represent a rate of change, or the slope of the tangent line, which is acceleration. So I just wanted to summarize these two ideas a little bit here for you, that if acceleration is positive, that meant the velocity function had to have been increasing. And if acceleration is negative, then that meant that the velocity function had to have been decreasing. Because right here in this section, these are representing the slope of velocity's graph, okay? Or the slope of the tangent lines on the velocity graph, okay? They're representing the rate of change on the velocity graph, okay? Now I said that in 3 different ways because I'm trying to get to the same idea that I keep talking about the derivative. All right, so moving on from here. In general, S of t is your position function. So the velocity is your rate of change of the position vector. Position function. I don't know where vector just came from. You should laugh at me on that, okay? So velocity is the derivative of the position because it's the rate of change of the position function. Okay, acceleration is the derivative of velocity because acceleration is the rate of change of velocity. Therefore, it's the second derivative of position. Okay, we're going to keep saying rate of change, rate of change, rate of change. All right. So with that, let's get into some examples. Let's try to finally get into, so what the heck is happening? So in this example, poor Bugs Bunny is all tied up. If you've ever watched a Bugs Bunny cartoon, Yosemite Sam has tied up Bugs Bunny and has put it on a super, super high board and is threatening to push him off. But funny Bugs Bunny, if you read this, has decided to just jump off the board, okay? It's Bugs Bunny, what could happen? He always bounces back. So if we look at this, Bugs Bunny's position is given by the equation negative 16t squared plus 16t plus 320. Now, the important thing there is that this is a position function. It's really important for us to understand that we have not been given velocity, we've been given position, okay? So as we look at this, our very first question is, what's the displacement from 1 to 2? Okay, now if I were you, to make your life easier, I would grab my nice little graphing calculator or go to Desmos, and I would definitely be putting in negative 16t squared plus 16t plus 320, graph it, why not? And then as we need to find values, you can let your calculator help you out with it a little bit, okay? But for the very first problem, if I need the displacement from 1 to 2 seconds, I need to know how has Bugs moved from a time of 1 second to 2 seconds. Where's he at? So what's happening then is I need S of 2 minus S of 1. So in the interval that we've been given, our displacement means that the starting value is S of 1, the ending value within this displacement is S of 2. So I need to know what is S of 2, and it's 288, and S of 1 is 320, and I'm just letting my calculator do that work for me. Remember, you can hit second, trace, and then the very first option is value. Plug in 2, plug in 1, get out those numbers, okay? So you should get out a negative 32, and before we keep going, I wanna know, what does that mean? Negative 32 what? Well, first of all, it's negative 32 feet, okay? And why is this negative so important? Because the negative tells us a direction. Bugs has jumped off of this nice little board here, right? And is going down, okay? If you had 32 there, then you would be telling me he traveled 32 feet, but you've left off in a really important part. What direction is he going? Okay, if you wrote 32 as your displacement, that meant Bugs Bunny, the object, has traveled up, okay? Well, Bugs Bunny has not gone up, he's gone down. So the negative 32 is really important because it's telling me from 1 second to 2 seconds, Bugs Bunny has traveled 32 feet closer to the ground, okay? All right, so let's keep on plugging away. When will Bugs hit the ground? This is a really great question from Algebra 2. When's he gonna hit the ground? Well, what will his position be? When he hits the ground, S of t is gonna be 0. His position will be 0 feet from the ground. So I need us to solve this lovely quadratic. And you have, fortunately, many ways to do that, okay? One way Quadratic formula, another way you could graph this, another way you could try to factor it. You could even use completing the square if you wanted to. Okay, fortunately for us, this problem actually does factor pretty easily. Okay, so I'm going to factor out -16, and I believe that leaves me with -20. So I have -16 times t minus 5, t plus 4. Now I'm going to use a little zero product property to figure out where would that be at, and that would be at t is 5 or -4. Now one of those makes absolutely no sense, right? In the scheme of this problem, there has to be an implied domain, that there's no way we could have -4 seconds. That would mean before bugs could even potentially have been tied up and put on this board. So my only logical answer is that t is 5 seconds. So poor Bugs Bunny, he's got 5 seconds before he hits the ground. Okay? All right, so moving along here. So what is Bugs's velocity at the impact? So in other words, okay, keyword here that I've got to look at, velocity. Okay, his velocity when he hits the ground. Okay, well, first of all, just knowing I have to calculate velocity means that I need the derivative or the rate of change on his position. So the rate of change, meaning the instantaneous rate of change on his position function, we can find this out pretty fast because we now have the power rule. So I need the derivative of -16t squared plus 16t, and that is going to be -32t plus 16. Okay, now that doesn't answer the question yet, because that's just telling us the velocity function. What does impact mean? This impact. That means when Bugs hits the ground. Now, for my friends who have never watched Bugs Bunny, Bugs is his name, right? That's his nickname. Okay, so I'm not talking about bugs that are crawling around, right? So when Bugs hits the ground, do we know when he hits the ground? Oh, yes, we do. Because in question B, we found out that that's at t equals 5 seconds. So what this question is asking for, technically, is what is v of 5? What is his velocity when he hits the ground at 5 seconds? So that would be -32 times 5 plus 16, and I have a -144, okay? So if you're with me on the -144, that's awesome. I'm really happy about that. But now we need to give the units. So don't forget, this is a rate of change. So this is his position versus time. So position, what was his position being measured in? Feet per time, which is seconds. Whoops, sorry about that. Okay, what does it mean that there's a negative? What's his velocity? Okay, now this is different than asking you what's his speed, right? Remember, velocity gives us the motion and direction. So we can now say what -144 feet per second means is that Bugs Bunny was traveling 144 feet per second down. The negative tells us, you gotta think Bugs Bunny is traveling vertically, the negative tells us down. So maybe you need to make a note for yourself, just since this is the first time we're doing it. Okay, he is traveling 144 feet per second down. That's what the negative means. If you don't include the negative, we have a problem, okay? If the negative's not there, it means he's going up. That would be bad for this particular problem, okay? So now we get to the next question, and it's asking us his speed. Okay, well, cool. We've already done all the work for that. Speed is the absolute value of velocity. And now again, they're asking us at impact, so we already found that. So I need to know what is the absolute value of -144, and that gives us 144 feet per second. So if somebody said, well, how fast was Bugs traveling when he hit the ground? 144 feet per second, which is different from the velocity at which he hit the ground, because the negative tells us what direction he hit from. Okay? All right, so last question. Okay, here we go. Find Bugs' acceleration as a function of time. So in other words, what was he accelerating at? Okay, so if I know v of t, which I do, right? V of t is negative 32t plus 16. Okay, acceleration is the derivative of velocity, which just gives me negative 32. Okay, this is going to be really important for my physics people right now, and I'm pretty sure all of you have either had it or are in that class. I want you to tell me the units right now. If velocity was a rate of change, and our rate of change was feet per second, remember that acceleration is the rate of change of velocity. So what this would mean is that, okay, we'd have our velocity, v of t, versus time. Okay, so what is that? V of t was feet per second. So this comes out to giving us feet per second squared. And some of my physics people should be like, oh, wait a second. So acceleration is negative 32 feet per second squared. And I would bet that that means something to some of you when you talk about acceleration, okay? Gets into gravity. Yeah, there's all kinds of fun stuff that's going to come about. All right? Okay. So with that, ladies and gentlemen, there's just a general example, okay? It was pretty straightforward of asking you questions. The last one that I want to go over is example 3, and I would highly encourage you to try this before you listen to me going over it, because quite frankly, some of this can get pretty confusing, okay? Now, before you get going with it though, just as a few things to point out, I want you to realize that this graph is not a position graph. This is a velocity graph. And it's of something that is moving along the x-axis, okay? So we're plotting the velocity as it's moving horizontally, okay? So whatever this object is, it's moving all over the place, back and forth horizontally, okay? So if we stop and think about what that means for a moment, just take the velocity for a moment and just summarize it. If your velocity is positive and it tells us direction, then there's only one direction that's going to make any sense here, okay? And so I'm looking at this. If our velocity is positive, actually, I want to change something for a second. If our velocity is positive and we're moving left and right, then the only thing that makes sense is that we're moving to the right, okay? Velocity tells direction. Which direction, right or left, is positive? It would be right, okay? Now, on the flip side, if our velocity is negative, okay, well, velocity tells direction. We're moving right and left. Left is negative, okay? And most importantly, if your velocity is 0, then that means you're not moving right or left. So when I say you, the object is not moving right or left. So right now, my velocity is 0. I'm not moving anywhere. I'm not going right or left. As soon as I start to go one direction or the other, now I have a velocity, right? So keeping that in mind, pause the video and answer the questions that follow. Okay. I'm hoping you actually paused the video and answered some of these. Okay. So let's use what we know and let's see how far you got. Some of these questions definitely get a little tricky. Okay. So my highlighter, which way does the particle move first? Well, here's where the particle is moving first. What are those outputs? If I'm looking at those outputs, V of t, when we start off, is negative. All of the outputs along here are negative outputs. So if I've got a negative velocity and it's telling me direction of something moving horizontally, then this object is moving left. Okay. All right. Let's get rid of that. When does the particle stop? So if the particle is stopping, then that means it should have no velocity. Now, when I say no velocity, I mean a value of 0. So when do we have on this graph a value of 0? There they are. I got 4 of them. So t equals 0. Looks like 3, 7, and 10 seconds. Okay. All right, I'm gonna erase those off of my pretty picture. Okay, when does the particle change direction? Okay, so to change direction, that means that we have to be changing from right to left. Okay, we're still talking velocity, right? In order to see a change in direction, we need a difference of positive velocities to negative velocities. Remember, once again, velocities give a rate of change and these signs tell the direction. So if that's the case, then let's take a look. When does it change direction? Right here. This is the only location where we have negative outputs. So negative, negative, negative outputs to positive, positive, positive outputs. So when does that happen? At t is 7 seconds. And this is where we are changing, well, v of t changes sign from negative to positive. Okay. All right, moving on. How are you doing so far? Okay. When is the particle moving left? Okay, left on our graph would be negative values, right? So that means that the velocity has to have negative numbers. So if I'm gonna look at this, I need v of t to be negative. So where are the outputs negative? Okay, you gotta be careful with this answer. Now, all of these would appear to be negative, but I'm gonna tell you there's a spot. There's a few spots. We've gotta be careful. If you write down an answer of 0 to 7, then you've missed something. The particle is not always moving left. What happens right there? The particle stops. This velocity here is equal to 0. So we can't include that as part of our answer. So the particle is moving left from 0 to 3, and then again from 3 to 7. And I can even put the little union sign in there. I cannot include 3. I can't include 0 or 7. So don't put any brackets. Or if you're writing less than symbols and stuff, better not have an equals. Okay? All right, so we keep on going. When is the particle moving right? Okay, well, right would mean that v of t has to be greater than 0. We need a positive velocity for this particle moving right and left. So we want to move to the right. So that means we need a positive sign. So that would be any of these are positive outputs. So our answer would be 7 to 10. Do not include 7 and 10 because at 7 and at 10, we have outputs of 0. Okay. All right, so far so good. Let's keep on going. When is the particle speeding up? Ooh, look at that. That word speed is coming up. Okay, so speed is the absolute value of velocity. Okay, so the easiest way for me to think about this, since I'm new to the whole velocity acceleration and all that good stuff, is that I want to take the absolute value of this. So let's look at this graph up here. If I take the absolute value of all these outputs, like here's a -1, the absolute value of that is 1. Here's another 0, right? But here, -1, 2, 3, 4. The absolute value of -4 is going to give me a 4, and so forth. Okay, what I can get relatively quickly, and that should have been straight across, and then the absolute value of a positive is still there. Okay, what I can see right now is a speed graph. So in blue, this is speed. Okay, so I want to know when is the article or particle speeding up? Okay, so when is the graph increasing? Well, I feel like it's increasing here, 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 and there it is. When is this speeding up? From 0 to 1, okay, from 3 to 4, and then from 7 to 9. There we go. Now that's going to help me answer the next question too, of when is the particle slowing down? Okay, well, if it's slowing down, then that means my speed has to be going negative. So my speed is decreasing. Okay, well, speed is decreasing in all of those. So if I want to write my answer for that, thinking, what is that? 1 to 3. Okay, 4, 5, 5 to 7. And then 9 to 10. Okay. All right. So H, when is it moving the fastest? Okay, so what is this meaning? What is the maximum speed? When does that happen? Well, that happens actually on an interval, and it happens in here. So the particle is moving the fastest in between that 1, 2, 3, 4, and 5 seconds. All right. Okay, when is the particle moving at a constant speed? Okay, so constant speed would mean that there is no change in the speed. Well, and if there's no change in the speed, okay, in other words, it's remaining constant, well, I'm going to still go with 4 to 5 seconds. Okay, and then let's get down to acceleration and graph the particle speed. I actually already did that for J, okay? So I already did that in blue, okay? But now let's graph the particle's acceleration, okay? So when it comes to acceleration, let's come back down to this, okay? I need the derivative of this graph. Okay, so if we're going to look at the derivative of this, we need to plot out the lovely slopes. So what would I think this slope is going to be from here to here? Looks like it's probably a -1. Okay, so if I back up, so -1. The slope of this next area here, okay, that looks like it's going to be, I don't know, what, 1/2? So if I come back to this, that's positive. Okay. Next part, what is the slope of this value? So that is a negative value, right? So it's going down 1, 2, 3, 4 over 1, so -4. So something like this. Okay, keep on going, and now I'm looking at this area. What's the slope of that? 0. Okay, now we've got a bigger area. So if I'm looking at this line, what is the slope of that? And we've got a change of what, 1, 2, 3, 4, 5, 6. It went over 3, so that would be a slope of 2. Okay. Now we have a next little area. The slope in there is 1. And then lastly, it looks like my slope is a -3. So what I have just graphed in purple is my acceleration graph. Okay. Now, we are going to round this out now because this was a pretty long video, and we're going to definitely talk more and more about this in class, specifically coming up with like, okay, so what's going to be the easiest way of us really looking at our speed, that we don't have to necessarily go and graph out the speed function to figure out where the particle would be speeding up, slowing down, where it would be at the fastest, and so forth. Okay, but for now, we're going to call it a quits, and hopefully we have a pretty good understanding, at least going into class next, on position, velocity, and then acceleration. Okay, mixed in with a little bit of speed and displacement. All right, so everybody have a great day, and we will see you in class to take this further.